used in phones and laptops. So anyone knows how many PCB layers will be present in the smartphone we use or the laptops we use? You can try to answer in the chat box. Usually in the cell phone there are multiple layers of PCB since there are multiple components required for functioning properly. So people, there are actually 8 to 12 layers of PCB. Imagine the complexity. There will be 8 to 12 layers usually in a cell phone. And yeah, here is the diagram shown the comparison between single sided PCB and different layers of PCB. So single sided PCB, there's a substrate, a copper layer, and the solder mask to protection. Whereas in double sided PCB, we have two copper layers. In multi-layer PCB, we have copper layer and a separation and a substrate. Then we'll have multiple layers of copper and multiple layers of substrate put between them for electrical insulation. We'll make a multi-layer PCB in such a way. Then this detailed diagram shown how we connect components in a PCB in multi-layer PCB. So there is core, whereas and there are again copper pathways. Again there's core, and we'll put again copper layer. Such a way it is made. These are the traces on the top layer. So here is a detailed concept explained in this PCB diagram. So you can see a path, right? There's a path shown here. These are actually called vias, vias, vias. So there are actually called vias. These are actually paths between two layers. If I want to connect PCB layers in this, I want to connect this trace and this trace. I'll start the layer like this and go into this. There are connections between them, so you can connect again components between multiple layers. Then you can get back into the top layer and communicate between different layers with the help of wires. We'll look into this detail in the next few slides. So first let us see why we need multi-layered PCBs. As we have discussed, there are complex circuits. Like take an example of a cell phone where there are multiple components. So multiple components have multiple pins and multiple connections will be there between them. So placing all the connections on a single layer compact design is not possible, right? So a cell phone is in the hand, right? We can place it in our palm, right? So every connection to be placed in such a small space is difficult. With the thousands of connections, modern circuits demand thousands of connections. So space provided by single layer will not be sufficient. So we use other layers. So we use multiple layers to overcome this problem. So there will be multiple layers. So I'll connect components in one of the layers. The place is not there. I'll go from layer 1 to layer 2 and give a path there and come back to layer 1 and connect the components. That is where the wires I have told will be using. So what if a PCB demands a connection between two different layers is where the wires come. A via is a small hole in a PCB that is filled or coated with copper, so it conducts the electricity. Just a moment, Satvik. I think everyone are muted. Yeah. Okay, I'll continue. Yeah, okay. Yeah, as we are seeing important different types of wires, there are through hole wires. So So yeah, there are three types of wires present. One is through hole wire, and another one is a buried wire, and another one is a blind wire. The through hole wire is from the topmost layer to the bottommost layer. It connects all the layers, whereas a buried wire is present between few layers, maybe between a third layer and a fourth layer. Whereas a blind wire starts from the topmost layer and present up to some like fifth layer or sixth layer. So the connections are usually like we'll go from like this. We'll start from the top layer and go, and we'll continue in this layer the connections, and we can go into the next layer through another buried wire, and then continue in this layer. So such way of connections helps us to save the space and also connect all the important components like this. We can go from the top layer to the bottommost layer. So we'll place the wires wherever necessary. Wherever we need space, we'll place wires and connect through the another layers. That is what wires are used by. There are also different types of wires called thermal wires. When we are placing many components in such a small space, overheating is a common problem in electronics. So the components get overheated. So we need to get rid of this heat. So we use thermal wires. They are actually holes in the PCB board used to spread and dissipate heat more effectively. They are present between the layers or through, like they may be present anywhere. So wherever an important component is placed, so to transfer heat from that component, we'll place these holes. So it will get us to dissipate heat more effectively. And yeah, there are also non-conductive holes in the board, as we can see in the example, which are called non-conductive or non-plated through holes. See, these we have already discussed wires. These have copper paths. When we are placing copper paths, we get electrical connection. Where there is no copper path, it's usually insulated path. We do not get electrical connection. These are used for mounting the PCBs. So there are also non-plated through holes that is non-conductive through holes. So do not confuse between the through hole paths and through hole wires. So through hole paths is used to mount the components, whereas through hole wires are the holes in the PCB, copper pathways in the PCB between the layers. So they help copper paths between the layers do not support any components, just electrical routing between the layers. So through hole paths usually support the components. In general, allow connection from top and bottom layers. They provide mechanical strength to hold the components. Yeah, since we have discussed a lot about PCB, we have discussed what is a PCB, why we need a PCB, what is PCB made up of, how the connections will be there in a PCB. So multi-layered PCBs, why do we need multi-layers, and how do we get rid of heat as well. We have seen a lot. We'll see how to design one of the PCBs. So in earlier days, usually when this manufacturing scale was not there, usually PCBs are made with hand only, which is very tiring to hear. So copper boards were coated with a protective resist. They draw everything by hand on paper or film. So they'll place copper and remove unwanted copper with acid itself. Holes were drilled manually, and then components were soldered by hand to complete and all. So this very long process. So don't worry, we have the automated processes these days, which we can use very effectively manufacture PCBs. First, the circuit is designed in softwares. There are multiple softwares available like ECEDA, KiCad, LTM. Today we'll show you how to use ECEDA. Then the PCB layout is generated digitally in the software itself. Then the data is sent to the manufacturer. Like files will send to the manufacturer. Then he will use machines to print the circuits, make copper layers, drill holes, blade wires, etc. There are also machineries to place the components in the place. Components are placed using the pick and place machine. It will directly place the components at the desired location. No human work is also required for such a technology is available. Boards are soldered in reflow ovens where at a time everything will be soldered. So we are using computers and manufacturing with high precision. We'll show you which software to use. It's going to be ECEDA. So a software usually produces, when we make a schematic diagram, it usually produces PCB layout so that we can export some files. I already told you some files are being sent to the manufacturer to know what is the PCB he is going to manufacture. Those files are called Gerber files. I'll also explain what are those in detail. Then we'll pay money, of course. Yeah, what are schematic layout files and BOM? These are four important terms we need to remember in the software. A schematic is a circuit diagram. Basically, uh, it's a circuit diagram showing which component is connected to what and what pins and all. It will show. So the PCB layout is the real physical placement design of the component. If we can select the shape and all, we place the components. That is what our final PCB will look like. It's called PCB layout. It shows where components sit and how copper tracks runs on the board. And after layout of PCB is ready, we'll send this. Will the software produce the Gerber files? These are manufacturing files. Tells exactly how to build a PCB and all. It's like a blueprint for production. And finally, bill of materials. It's just a list of all components we used in those name, value, quantity, part number. Also, sometimes prices also will be there in the software itself. Okay. Now let's see how we set up of ECDA. I think everyone has maybe you have a laptop ready for it. You can go to your browser and search for ECDA. You can just search for ECDA. It's just an online website. When you open it, it's sign in page. You can create your account or just sign in with the Google itself and continue. Then it will be shown like this, where you will be signed in. You can directly design in online. You can use, there are two different types of versions in ECDA: STD, standard student version, and also pro version, where student version is sufficient for many of the basic projects we are going to use. There is also a downloaded version, but we can go with the online version itself. Before going into the CDA, let's look at a circuit so that we can prepare a PCB for that one. For the circuit part, we are going to look at, as we have already sent in the group, you can once go to a website, the Walkway website. You can just type Walkway and you'll go and sign in. You'll found their page in the browser. So come below, you'll see featured simulation projects. We'll explain one of these projects and we'll make a PCB for that one. We have selected minipiano.ino. You all can open this in your laptops as well. You can go into the Walkway website and go below, scroll below, and you can find the simulated projects ready for you already. And this is what the project is it's going to look like. So this is a basic circuit with the basic code present here. We'll just look what the circuit does. It's just like a piano where we can press the buttons and we can get different types of sounds for each button. It works like a piano. So it is made with an Arduino Uno board and a buzzer or a speaker is used. So these are push buttons and the wiring is done. So the buzzer is attached to one of the wires and common ground is given to all. And you can see the push buttons are attached to different pins. These pin numbers will be there in the code itself, and also the speaker button will be there in the code. This is a basic description of the mini piano for Arduino. I'll explain the code in detail so that you can understand the circuit more. Hope you all can see the code. I just copied it and placed it here. So the first line includes hashtag include pitches.h. This is a common library. It usually what it contains is, so in keyboard different notes will be there, right? They'll call C4, D4, such that they have characteristic properties. They have different frequency. So here some of the notes are mentioned. G4, A4, B4, C5 and all. Each number will have different frequency so that it sounds differently. That is what hashtag include pitches.h contains. It will have the frequency number for example, if we take F4 to be 242 hertz. So whenever we use the code with hashtag include pitches.h, as when note F4 appears, it usually refers to 242 hertz. Then we'll look into the code. One second. Yeah, uh, hashtag define speaker pin 8, as we have you can see in the walkthrough page, the speaker is connected to the pin 8, so we are defining the speaker pin to be number 8. Then we are defining an array button pins. We named it button pins. It's an array with 8 switches. Since we are using 8 switches in the circuit, we have placed 8 numbers for them. These numbers are usually the pins where we connected the switches. You can see the 12th pin is connected to one of the buttons and 11th pin is connected to one of the buttons and so on. So it is an array. Basically, button pins is an array we are creating. And button tones is also an array with the frequency values for different pins. So whenever you place a button pins, a number in the box, it refers to the number. If you place 0, it will get to the first one. It refers to 12. If you place 1, it will refer to the 11. If you place 2, it refers to 10. So on 0, 1, 2, 3 up to 7, referring to the 8 switches in the circuit. Similarly, corresponding to the 8 switches, there are 8 frequencies for each switch, so that each switch sound differently. Then we are defining constant integer num tones. So it says size of button pins by at the 0th index. So if I already told you, the button pins array refers to 0th index is 12. If you are taking size of this number to be 1 byte, then the size of button pins will be, you can think of it, if I'm saying the 12 is of size is of 1 byte, then there are 8 such numbers, so the size of button pins will be 8. So 8 by 1, the size becomes 8. So the num tones is already 8, which we know. So the constant integer num tones is already 8. So we get constant integer num tones is equal to 8. We have just set up this for extension, which we are not using now. This is given this, like, you can also ask, we can directly set up num tones equal to 8, right? Why are we using size of this and size of all? If you want to extend the number of switches and all, you will add the numbers, right? If I'm using 10 switches instead of 8, I'll add different numbers, right? So in that situation, without changing only, this code will update. Then let's look at the setup function, void setup for I equal to 0 to I less than num tones. Already we got the num tones to be 8. So from 0 to 7, the for loop works such that button pins of I is connected to input column. So the pin mode defines what the pin is actually connected to. So button pins, we have decided the numbers, right? 12. If I'm taking the 12 here, it's connected to input pull-up. The switches we are using, right? The switches actually work like this. If we are symbolizing this as a switch, and we'll place a input resistor. The circuit will be like this, and I'm connecting to the ground here. Ground is just 0 voltage. I'm placing this resistor here, so I'll place the resistance here, and I'll connect to high voltage. So our pin will be here, and this is the button we are using. This is the input pull up mentioned here. So if I press the switch, if I press the switch, it will connect to the ground, making the pin voltage to be 0. So the pin voltage will be low. If I'm opening the switch, the pin is connected to the higher voltage, so the pin voltage will be high. You got this right? We are using a resistor here. If I press the switch will come into contact here. If I'm pressing the switch, the contact is made with the ground, so the pin will be at the low voltage. And if I'm not pressing the switch, the pin will be at some high voltage, some number based on the voltage shown here. We are also mentioning the for the speaker pin. For the speaker, we use the 8 pin, right? So 8 will be mentioned. So we are mentioning it as output, and these buttons pins we are mentioning as input pull up resistor added. Then we'll go into the loop. Initially, take pitch to be 0. Pitch is usually the frequency number. I told right, the different types of notes, there are different types of hertz value, frequency values. Take note C4 to be 242 hertz. So initially I'm placing pitch equal to 0. So I'm using a for loop here. If I start from 0 to I less than or equal to I less than 8, from 0 to 7, digital read is a function which we have also covered in previous sessions, which reads the voltage at the pin. In the IoT session, we already covered what is a digital read. Digital read is a function which reads the voltage at the button pin. So if I am taking button pins of 0, that is the 12th pin, it digital reads. If the voltage is low, that means it says the if condition is voltage is low. That means then if the switch is pressed, it connects to ground, the voltage will be low, right? If the switch is pressed, pitch is equal to button tones of 0. Corresponding to 12, the note is C4. So the pitch will be now 242. So it's a for loop. It checks from the first switch to 8th switch. Whatever switch is pressed, the pitch will be that corresponding hertz value. If pitch, since pitch is a number, if statement will give true, it will enter this. Tone is a function for speaker. It is used to give the speaker the pitch value. So the speaker will get this 242 hertz. Usually a wave is created at that frequency, and the buzzer will respond based on the wave. A square wave is produced actually at the 242 hertz frequency, which will make the buzzer sound in such a way. If no button is pressed, no sound should come. Simply says no tone. One second. Sorry. Yeah, this is what the code mentions. You can look the code we have already explained. So if I am pressing this button, the voltage at that pin will be low. Going into the code, then corresponding frequency is got into that speaker, and it sounds in such a way. Each button has a different frequency. So this is what the circuit is, and we'll be going to design a PCB design for this. In the ECEDA software, you can keep your ECEDA software and design simultaneously, or listen perfectly for now, and you can do it on your own. From here, my teammate will continue. Anand,
Yeah,
you can take over.
yeah. Hello guys, I'm Anand. I'll continue from now. First of all, I'll share my screen. Yeah, I hope you can see my screen. Yeah, this is how it looks like. Yeah, the the easy dashboard looks something like this. And first of all, we need to create a new project. Before that, let's go through some user interface of EasyEDA. First of all, for creating a new project, you need to select this option, new project, and you can also I'll demo piano. Yeah. So I created a new project here, and it will direct me like it will take me to this canvas. This is nothing but your schematic. The canvas will look something like this, where you will keep all your components and design your circuit. And for finding your components, there are two options. First thing is common library. Hope you can see this. I'll try to, yeah. You'll have ground, VCC, resistors, capacitors, uh, LEDs, and all those things. All the like some basic components. If you want some other like higher level components like Arduino or ESP32, like many other things, for example, an Arduino, you can just type that, you'll get that component, okay? And you have this LS, LC, SC parts, where you can find different parts in the section. You can order the parts. It will direct you to another screen. And you have this JCL PCB where you can order your PCB. Like JCL PCB is a manufacturing company, okay? And this is recycled pen. First of all, like why we need a schematic? You can ask me why we need a schematic. Like we have schematic, we have PCB layout, right? Like why we need a schematic? The main reason is we need to create a circuit first, and there is one like a better useful thing with this schematic. I'll tell you that later. You will get to know while doing PCB layout what is that. You can annotate your circuit in this schematic so that whenever you refer this again, you can easily understand your circuit or you can easily debug your circuit. That's the main reasons, like some reasons for using schematic first. First, you need to create the circuit, then export it to your PCB layout. First, we'll create our circuit, okay? You will understand, eventually, you will understand it. So, like our final output will look something like this, okay? It will look something like this. And first of all, we'll keep some components in, like all the components. And keep in mind that in the WoW key, like WoW key simulator, we used Arduino Uno, but here we are using Arduino Nano. Take care of that. Like I'll just search in Arduino Nano. Um, yeah, we got that. Just place it. There is some one option to place it. Just place it. Escape. And we need 8 push buttons. Okay, you can just click on that and it will 8 push buttons. And we need one buzzer. I'll take it from this. We are using this processor. I'm copying this. I'm pasting it here. Now we have all the components we need. Okay. Yeah. This is our all the components. Okay. Now we need to connect the wires. How we'll do that? We are going to do that with wiring tools. Okay. And like there are two sections in this, like wiring tools and drawing tools. I hope you can see this. Wiring tools will provide you many options like wiring, bus tool, net labels. I will explain all like everything. Just like eventually you will understand about every tool. I'll explain that whenever they demand. And there are some drawing tools there. Okay, like these drawing tools are for annotating your schematic, like making it better, like you making it look better. You can add a bullet, sorry, an arrow like this. You can annotate it. Like whenever you revise it later, you will understand it better in a better way. Okay. First, for doing wiring, like wiring, right, I'll just delete this. You need to click this option or just press this W hotkey. Okay. And just zoom in. Just I'll, mm, you got the wire and you can connect it wherever you want, like this. Okay. And like yeah, we can just do in this way. I'll just delete these things. Okay. We can do connections in that way. But making connections for many components like it requires 20 to 30 wires, right? It will become clumsy, a lot clumsier. To avoid that, this easy idea will, like every uh, PCB designing software will give you an option like net labels. Net labels are nothing but you will just keep your name. Just name it. Name the pin. Name that pin. Drag it. Name that pin. For example, I'll name it as 3. Net level. So 13. And I'll just keep one more here. And I'll name it as again. Now these both are connected. Without wire we just connected it. It's a better option, right? You will be having better visibility and all. So we use net labels in this. And in our project we'll use only net labels. There are some other tools like bus entry and bus tool. Like many PCB designing, like many people won't use these tools, but the use with these tools are like uh, to ensure that we are using net labels. So here we use one net labels. Here we use one net labels, and like these are connected. We will ensure in this way. So we use net labels. Like this is not good actually. Okay. And now we'll make our connection. Okay. Beautifully. Wait a minute. Yeah. First of all, I'll place the components neatly. Just give me some time. Just give me 2 minutes. Yeah. Now what I'll do is first I'll use one wire for ground connection. There is one ground here. I'll use a wire tool. I just press the hot TW. This ground. I hope you can see this ground for ground. I'm just connecting it to all these things. So that whenever you press this push button, it will go to it will go 0. I connected the ground, and now I'll use net label for all other connections. Okay. So we need to connect from pin number 5 to pin number 13. I'll tell you the connections now. So first of all, I'll be placing some net labels. Then I'll keep my net label here, one here, here, one here, and I'll change the names later. Okay, don't worry. 3 are okay, and one more here. We also connect one ground here. Okay, and now I'll change the names. Okay, I'll change this to 1, 2 like that. I'll delete this 1 and just double click and change it 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now I'll change these also 1, 2, 3. This is only I'm making only the connections. Don't worry. 7, 8, 9, sorry, sorry, 9. Yeah, we are done with the connections. And there is one thing like we need to check like there is one tool known as ERC in every software. There will be one tool known as ERC for checking the errors you made. So we missed one thing here. We will check with ERC and we'll take care of it. And then next, you know, like I left some connections, like I left some pins, right? We need to connect them to no flag. So I hope you can see this, these symbols here. It is showing us error. So you haven't connected this, you haven't connected this pin, we haven't connected this, right? So we will use a tool known as no connection flag. The main purpose of no connection flag is to tell the software that this I'm not going to use this pin. That's it. Just simple. I'm not going to use this pin, so I'm keeping a no connection flag. This no connection flag. Okay. Yeah. Yeah, it's online only. You just need to sign up with Google account. Yeah. Now, you can see that there are no errors. Everything is good. I'll save this first. Okay. Yeah. We are done with the connection. It looks like something like this. Yeah. We just connected the push buttons to your Arduino Nano. We connected the buzzer. Every connection is made. Yeah. We are now good to go to other parts like PCB layout and all. Now, before going to PCB layout, I want to tell you one thing. uh, about footprints. So footprints is like every animal will have some footprints, right? Likewise, every component will have some footprints. Footprints are nothing but the exact geometry arrangement of pins. Like every component will have pins, right? Treat them as legs, and they are arranged in some geometry, right? And while doing okay, I'll tell you with small example. For example, there are two companies, X and Y. Uh, I hope you all know about this chip 555 timer. If you don't know, just consider it as like a small chip. And this thing is made by two companies, and both companies footprints are different. Like they keep their they keep their pins arrangement differently. And you are having the component from X company. By mistakenly, while creating your PCB, you use the pin arrangement of company Y, and you send it to your manufacturer, and your PCB came to you. So now the issue is the pads for 55 timer on the PCB won't match with the component that is having with you. That's an issue, right? We don't want that. So to ensure that won't happen, we will take care of these footprints, and like to know where the like what are the like which type of footprints are using for the components. You can just click on the component and just scroll it down. I hope you can see this part. Footprint. Yeah, we are using this footprint. Since this is a demo, we are not using we are not having any components. This is a demo, so we're using random components. But when it comes to the real life, you should take care of these footprints. Wait a minute, I'll just change my screen for knowing more about footprints. Yeah, I just shifted my screen to slides. So footprints, like what are footprints? A footprint is the exact copper pad layout on a PCB that matches exactly with the component pin spacing and package. So it can be soldered correctly. If this pad arrangement and your component pin arrangement don't match, then you cannot keep your component and solder it, right? So to ensure this won't happen, like this error won't happen, we first take care of all the footprints. Okay. And yeah, assigning footprints is a very crucial step. If your assigned prints are not matched with the components you solder on it, yeah, then you will be in this state. We will come back to easy EDA and explore about PCB layout. Okay, we are done with the schematic. I'll just change the tab. Yeah. I hope you can see the screen. So this is how it looks like. Sorry. Okay. For shifting to PCB layout, first you need to. I hope you can see this option. I'm pointing out this convert schematic to PCB. So before converting schematic to PCB, first you need to save it. Okay. Just press Ctrl S. Connecting to server, it's saved, and just click this option. It will shift you to a new screen known as. This is what we call as PCB layout. I'll just zoom out, and this is all your components. I'll just keep and this pink purple color line outline is nothing but your board outline. I mean your board looks like this. I mean after manufacturing your board looks like this. We can edit this later. First I'll keep these components inside the board. And the other thing is like at the start of my session, like my part, I told you what is the most important purpose of schematic, right? Like I missed that part. Like I didn't tell you. I told that I'll tell you in PCB layout. So the main reason is I hope you can see these blue lines, right? These blue lines here. Uh, it is pointing out from pin number D9 to T8, this part. So it is showing all the connections there you made. Like you made these connections here, right? It is showing all the connections. I mean, it is indirectly telling you that you need to connect this. Like, what is the purpose of this? Like, while doing your routing part, like while you connect this, while you keep traces, you might mismatch other pins. Like instead of connecting these two, you might ended up in connecting this with key 4. It will happen when you deal with some thousands of connections. It will happen. So to ensure that won't happen, like engineers design a structured way for designing PCB. Like they'll create schematic first, they'll import it to PCB layout so that you will get these blue lines, and you call these blue lines as rat lines. Okay, you call these blue lines as rat lines. We call them as rat lines in engineering context. So this will show you need to make these connections, and you can just focus on routing. Okay, routing means I'll tell you what is routing. So just and you will be having two tools similar to schematic. You will have two tools and PCB layout also. I'll just zoom out. Two tools. I hope you can see this. Layers and objects, PCB tools. First of all, I'll go with this layers and objects. Yeah, yeah, sorry, layers and objects. Like it will make you like the main reason for this layers and object is it will try to sorry rat line. They are rat lines. RATLINE. Okay, rat line. So this will like the main reason for this, if you select this option, you can work on the topmost layer. If you select this option, you will work on the bottommost layer. If you select this option, you will work on the top silk layer. So it's selecting which layer. Like if you want to work on some X layer, you need to select that first. So for this session, we'll be using only top layer. So yeah, I'm selecting the top layer, and you'll be having these PCB tools where you have tracks, pads, VRs, text. If you want to keep some text in still, still screen, then you should select this. Uh, any symbols or any images, placing mounting holes. Like mounting holes are nothing but non-plated through holes. I hope Satvik told about these things. Mounting holes are nothing but non-plated through holes. Setting canvas origin. You can shift the origin anywhere you want. Measuring angle. So these are some tools which EasyIDEA offers to you. And what is routing? Routing is nothing but just like for placing tracks. For placing tracks, you need to select this option. It's nothing but you need to connect this. Wait a minute. Uh, um, yeah. For example, you need to connect these two. So this is routing. Connecting two pins is nothing but routing. We will get to know more about this in the slides. I'll just shift to slides. You'll get to know more of the definitions and all that. Yeah. Yeah. Routing. Routing is nothing but process of drawing copper traces on PCB to connect component pins according to the circuit schematic. Very simple, right? And the one more thing, every PCB designing software will have a tool named as auto router. If you click that option, then it will automatically route everything. So I'll tell you what is auto router. Auto router is a PCB designing tool that automatically creates copper trace connections between components based on schematic and design rules. But we don't use that tool because and we route manually. You can ask me, but why? I'll tell you. Because auto routing, like, it is not having intelligence, okay? Like humans have it, like artificial intelligence. These auto routing tools are not having intelligence, so they don't care about performance, noise, design priorities. Like there will be, like, when you are designing your PCB, there will be some factors come into the picture, like crosstalk, noises. Like this noise is very, very annoying thing. We should take care of all those things. And auto router what doesn't take care about those things. It will just connect the traces. So there will be many factors that come into the picture of PCB layout part when you do your PCB. So we should take care of that, and we generally avoid auto routing. Like for smaller circuits, we can do auto routing, but just avoid that. It's a best practice. And now, before going to the PCB layout, let's discuss some topics which will increase our circuit efficiency. Because you are routing manually, right? You should know some things before routing manually. I'll discuss that and I'll go back to PCB layout. Uh, First of all, place related components close together. You should place your components together, uh, because, like, components that work together should be placed close to each other. The main reason is length of the track. I hope you all know about this formula. Like even a 10th class student will know about this formula. It's a very basic formula. Resistance is resistivity times length by area. If you are having a big trace, like a longer trace, then you will, like, the resistance of that copper track is higher. Means it is going to generate serious amount of heat than required. So if the length is less amount of heat will be generated. If the length is more amount of heat will be generated. And placing this related components close together will reduce that heat generation. So yeah, take it. We should take care of that. And the next thing is figure out your trace widths. So, like, increasing area also will also reduce the resistance, right? So if your trace is having more width, then it is going to have less resistance, and it is going to reduce. So it is going to produce less heat. So, like, longer trace means less heat generation. So we should figure out this trace width. And for doing this part, like, there are many online tools to figure out your trace widths. So it will ask you for some question. It will ask you some questions, and if you keep them, it will give you, like, which track which to use. Okay, we are not, like, okay, we will just leave that. And the other thing is, leave enough space between traces. Okay, like, if traces are too close, they accidentally can connect during manufacturing and causing short circuits. So this is a manufacturing defect. uh, like, it cannot, like, there is some limit, there is some manufacturing limit. The minimum accepted value, like the minimum uh, space between two traces should be 0.15 millimeter, and beginner friendly values 0.25 millimeter, and we'll use this 0.25 only in our session. And this is completely manufacturing defect. I mean, the machines cannot go beyond this. The machines cannot print beyond, like, lesser than 0.515 mm. That's a manufacturing defect. And if you try to keep those traces lesser than those things, your PCB designing, like, your PCB design software will give you an error. Okay, and avoid 90-degree trace angles. So there are two reasons for this. First thing is, like, I'll tell you. First thing is manufacturing defect. So uh, the machines cannot print a perfect 90-degree curve. It cannot print like this. It cannot print this edge. It will miss some part. Okay. Wait. So it will miss this. It will miss this part. This edge. It will miss this edge. I hope you can see this. And it's better to do in this way. So your track won't get damaged, and your circuit works better. Okay. And the other thing is dielectric breakdown. So in high voltage circuits, dielectric breakdown might happen. Like if you know about dielectric breakdown, just yeah, it won't be an issue. But if you don't know, just leave that. So it might happen. Yeah. And using this 45-degree bends is, it's a better practice. And everyone will follow this. Every PCB designer will follow this only. They use only 45-degree bends. Okay. And make a power and ground traces wider. We already discussed that, right? Like making trace wider will reduce the resistance. And the main issue with power and ground traces is like power and ground traces generally carry higher currents. If something is carrying higher currents, then it is going to generate serious amount of heat. So to reduce that, we will just decrease the resistance so that amount of heat generation will be decreased. Avoid long traces. We already discussed that, right? Long traces have more resistance and also can pick up electrical noise also. More resistance means more heat generation and all. We already discussed this part. And this is avoid unnecessary vias because they will add some manufacturing cost. If a via is required, then keep it. Like if you are having no option, then you keep it. But better to avoid these vias because it will add some manufacturing cost. And yeah, do not route traces too close to the board edge. I'll tell you what is the main reason behind this. So when you send your when you are you should send like when you send your files when you send your PCB to the manufacturer, what they will do is they'll combine your PCB with other people's PCB with a method known as panelization. And after completing everything, they'll just cut it. They'll cut your board back because like to save some cost, like to save some materials, they will do this. And it is very hard to handle small PCBs. Like for machines, it is very hard to manage or do like manufacturing on small pieces. So what they'll do is they'll take a big copper sheet, like big parts, and they will design everything on that, and then they will break it. And if you route your traces close to the edges while cutting, those traces might be damaged. Sometimes it might get like the circuit might be broken. The copper might be, just flushed off, went off. So to avoid that, like we just route, we don't route closest the traces close to the board edge, okay? And keep power and signal traces separately. Uh, like the main reason is high power, power traces will carry large currents, right? And they can generate large amount of electric and magnetic fields. And every signal is nothing but every signal will be generated because of electric and magnetic fields only. So if you place sensitive signal traces beside power traces, then it will generate a serious issue. Like it will impose some noise into these sensitive signals, and the data in those signal traces might get corrupted. So to avoid that, we need to keep power and signal traces separately. The other thing is label your components clearly. So you should label your components clearly. It will help you while assembling the components on PCB. That's it, very simple. And yeah, this is one of the most important thing. Like every PCB designer will do this. Create a ground plane for all the connections to ground. Because like many PCB designs, many projects will have some, many ground connections, and this will reduce if you keep a ground plane. So ground plane is nothing but keeping copper everywhere. And okay, I'll tell you about this while doing PCB layout. Try to understand this. You are going to create a plane for ground, and you will connect all ground pins to this plane. Okay, this will reduce the complexity of routing and also reduce heat dissipation significantly. And this is a really very good practice. Yeah. And now we are done with the some concepts. These are really very basic concepts. I mean, to be frank, like there will be some hundreds of factors to need to take care of while doing PCB designing, and we are not discussing those. I mean, those hundreds of factors because they all require some prerequisites. I mean, we should know some other concepts like in depth Maxwell equations about crosstalk, and all those things, signal integrity, and all those topics. So, like we are skipping those part now because they need some requests. But keep in mind that every problem that arises in your PCB or everything that is disturbing your PCB arises because of only three things. First is manufacturability. It's manufacturing defect. I mean, machines cannot do that part. And the second thing is electric fields. Third thing is magnetic fields. Now every problem will arise because of two things. Like apart from manufacturability, every problem will arise because of two things: electric fields and magnetic fields. Simple. And yeah, like every factor is because of these three things only. And let's go back to easy EDA. Let's go back to easy EDA. I'll change my screen. Mhm. Yeah, I hope you can see the screen. Yeah, now we'll do the routing part. Okay. I'll explain about the ground plane in detail while doing this PCB layout. First, we need to place our components. Okay, I'll just zoom out this. Okay, I'll just so I'll first arrange the components clearly so that I'll place a related component closely and I'll do something. Just observe. I'm doing this all the time. Okay, so just expanding this. So I'll keep my microcontroller here. I'll keep buzzer here. I'll place all the keys here. I mean all the push buttons, arrange them neatly. Since it's a piano, I should take care of that. I'll leave these mountain holes later. Just taking that. Yeah, we kept all the switches here now. Push button then. Yeah. Now I'll do routing part. I'll change this board outline also. Yeah. Now I'll do the routing part, and we are not going to keep any pads or any vias in this section, or sorry, for this small piano project. I'll just do routing. I'll select this. I hope you can see this track W. Either you place hotkey W or just click this and it starts here. I used only 45 degree bends. I hope you can observe that. I'll do routing fastly. So I'm working on the topmost layer. Fishing issue. Some mistake here. Start from my I'll just zoom in. avoid 90-degree bends and all. And there are some, I hope you can see this kings happened here. We can just edit that. Just double click on that. It will automatically adjust even here. Just double clicking on it will automatically adjust everything. And even here. Yeah. So we are done with some connections, and for making ground connections, like these are ground connections. The connections which are left are just ground connections. For making those ground connections, I will just create a ground plane. Okay. So for creating ground plane, just you need to use this option, copper area E. Just click on that. Just leave the net for right now. Right now, leave the net. I'll explain about these things later. First, we'll create one plane. So you need to cover the whole board. Okay. Yeah. So we made one thing. And yeah. Yeah. So just open this tab here. Like that. I'm opening this tab and click on this outline. You will have this net top layer. We worked on the top layer, not on the bottom layer. Just select top layer, and the name of that ground, the plane is this, and we have to change this net actually. So we need to use this net. Uh, let's zoom in. Just click on this pin. You will get the name of the net U14. Copy that. I mean, uh, like the name of ground net for this component is U14. So we are changing that. We need to change that. Just copying it. I'm clicking this outline, and changing the net. I'm pasting it there. So it changed. And yeah, we got our ground plane. So I'll explain about this ground plane now in detail. About. So ground plane is nothing but like it will cover. Also, we are working on the top layer. So what it does is it will cover the topmost layer. It will cover the whole topmost layer except the traces. I hope you can see. There is some gap here. There is some gap, and I'll just measure that gap. There will be some measuring tool. So that gap is nearly 14.6, sorry, 7.0 symbol. Yeah, it is using some other measuring system. Okay, yeah, this gap is fine only. You can change measuring system also. Okay, so it is keeping that gap, right? So apart from your traces, apart from your pins and all, it will occupy everything. Okay, that is ground plane. And there are really like many different many users with this ground plane. It will effectively distribute the heat everywhere, since a ground plane, like think ground plane as a trace, a big trace having longer length and also more wider area, like it's having a big area, so that resistance will be really smaller. And since ground, like power planes carry large amount of current, you know large amount of, like less amount of heat will be generated, because the ground is the ground race is really huge. I mean, it is having less resistance. I hope you understood that. And for, like, in the case of ground plane, you will have this. It will provide you some options. The layer which you are working on, the name, the net, the clearance. You can change this clearance also. It is IDA clearance in mils, and the pad connection. So Obviously, initially we haven't connected any ground connections, right? But now after placing a ground plane, it automatically connected those grounds. So how it will connect those grounds? It will actually use some spokes. It's a kind of method for connecting and all. Just leave that for now. It just connected every ground part, like every ground connections. It already did that in the back end. Keep island, just keep it as no. Fill style solid. Like okay, I'll just explain about this. If you select this grid 45 options, your ground plane will look something like this. And this is actually a not good practice. We should use solid only. The main reason why this PCB designing tool is providing that is like in olden days, like scientists, like the one who used to create, who wants to create this ground planes, like they used to create these grids only because in those days copper is a very precious metal and is not widely available, and they don't want to waste copper, so they use these grids to save some copper. That's it. But nowadays there is no issue. We'll go with solid, even though it increase the cost. It's a better, like the best thing. Keep this improve fabrications to S. Log you can keep it anything. You will copper area. So we made our PCB layout also. I'll just zoom out and show you everything. Yeah, this is our PCB layout. We are done with the PCB layout. I hope it looks good. Yeah, and I'll save it first. And now I'll show you one thing. How your board will look after you will send it to the manufacturer. You order it. So there is one option for checking that 3D view. Just click on that. You will get your board. So after manufacturing, your board will look like this. Your keys will be placed here. Okay, this is PCBA. This is not PCB. PCBA, printed circuit board with also assembly. You can change this. No, this is your PCB. This is how you'll get your PCB. You need to place all the components here. You have this labels key 1, key 2, key 3, so on, like to keep your components in their respective places and all. So this is how your board looks like, and just change it to visible. After placing your components, it will look something like this, and like the buzzer is missing because this software is not having the 3D blueprint of buzzer, so it just kept it open. But this is your Arduino Nano and keys and all. I hope this is good. I mean, yeah, every PCB design software will have this option. So yeah, we'll come back to here. So we are done with the PCB layout. Now what we'll do is we'll export some files. Uh, like we will export some files which contain every information about, like every information to manufacture our board, and we should send these files to the manufacturer so he can process that information and send it to the machines so machines can print. And those I'll categorize those files. So there are three different set of files. Sorry, four different set of files. First one is Gerber files. Second one is drill files. Third one is bill of materials. Fourth one is pick and place. So if you want only PCB without components assembly, you need to send him Gerber files and drill files. Just click on this option. Yeah, check DRC. So there are no issues. And like someone asked about the price, so it will show you here. Like based on your design, the price will vary. And go for generate Gerber. It is downloading. Like it will be saved to your yeah, like your file manager. Okay, they will be saved to your file manager. And for generating bill of materials, just click this bill of material, like this option. And bill of materials is nothing but it will have the every information about all the components. Just export it. It is taking something. I don't know, like, yeah, just export this. It got downloaded there. And this option is for pick and place. Just export that also. And okay, I'll tell you, PCB for manufacturing PCB only, for ordering only your PCB. What? Bill of material does not include physical board copper pins. Yeah, yeah. There will be many options for manage your tracks. Just click on the track, you will have the width and all. I hope you can see it. Click on any track, you will get the information about the tracks. And about bill of materials, I'll just open it. It is having the information. You are using one buzzer, the name of the manufacturer, the footprints you are using, the quantity, the supplier, and also price. But here the price isn't mentioned. I think it's not having anything. And key also, it is having keys and push buttons. The cost of push buttons, the number of push buttons you are using, Arduino, the number. It will have all the information. Okay, that is. So for only ordering your PCB, you should send him Gerber files and drill files. And you can ask me where you'll find these drill files. They'll be inside Gerber files only. They'll be inside Gerber files. Inside this Gerber option, you'll find those things. I'll just sorry, got shifted. Yeah, they'll be inside Gerber only. Gerber files. Drill files are inside Gerber files. And below, like if you want to order PCBA, like your PCB along with the components assembled, you should send them two more set of files, bill of materials, so that he can order the parts, like the manufacturer will order the parts, and will assemble that, will assemble those things. And about this pick and place file, it will be having the information, like like where to solder those things, where you should keep the components and how to solder that. It will have every information of every coordinates information of your components, your pins and all, so that like the manufacturer will send this pick and place to a machine. The machine will process it and take the components automatically, place on your PCB. It will automatically solder them. So the main purpose of these files are like main purpose of pick and place is that. So I hope I'm clear with those things. And yeah, we are done with much part of our session. I'll just shift back to the slides. We are done with everything. Actually, our session is almost done. I'll just change the slides. Yeah, I hope you can see the slides. So yeah, and yeah, scan this for attendance. For attendance, you should scan this. I'll wait for some time, and meanwhile, you can ask your doubts also in the chat box. We will answer any doubts. And I hope the session is really engaging. So scan this for attendance. So, there is one trace. That won't be any problem. There is one trace passing from below the Arduino. That won't be any problem. Okay. Yeah, no, there won't be any stuff like that. I mean, this is very small circuit. There won't be any inference happening. Uh, yeah, I hope like we explained about this schematic and PCB layout very well, and about the tools also. Uh, yeah, you can just go with the attendance. Yeah, the price is really high. We can reduce the price actually. For example, you can see this. Okay, wait, I'll go back to so I'll go back to easy idea once. Share. So I hope you can see this. Like there is some unused part. Like we haven't used this part, this whole part. We haven't used this whole part. We can change the PCB board outline. I'll tell you how to do that. Just delete this and PCB tools, also layers and objects. Go for like there will be one layer known as board outline. Just click on that. We are going to work on that. Choose your track tool. And I'll just edit that. The cost will decrease. I mean, we can just remove the unwanted part. And now again, we have to rebuild this copper region again. I mean, the ground plane again, rebuild the copper. It got changed, right? Like we can optimize our cost actually with this. We haven't done that. I'll save this. I'll also show you the 3D view of this 3D. So the board will look like this now. I hope you can see. It's not good actually. And let's come back to yeah. And now I'll just export the W file. The cost is decreased somewhat, 5.7 to 5.63 like that. We can optimize those things actually. We can save the space. Since this is a demo, we just you know did roughly. Okay, I'll just go back to the slides for attendance. Yeah, just scan this for attendance. No, we haven't routed right. Like somebody asked about the close path too close to this, but we don't have any routing near the like near the edge, and we will keep the components after manufacturing the PCB. First, we'll manufacture whole PCB, then we'll keep we'll keep components on that, so that won't be an issue. Yeah, this session will be available in YouTube recording later. We'll do that. We'll upload it by end of day. Yeah, we can use another buzzers also. Like can use other buzzers. I mean, somebody is asking about it. There are many components available. I mean, I use some random buzzer. Like there are different sizes for buzzer. We can change that. Uh, yeah, I hope I'm clear. If you are done with attendance, you can leave. And before that, I want to tell you one thing. Like on 15th, we are going to start in the next section, session 4. We'll be starting a new project, GPS tracker. That is really interesting thing. Like really, it's a very good thing, really interesting. Please attend that also. And yeah, we also had some issues today, internet issues. I'm sorry for that. We are sorry for that. And please join that day. It is really good. Like I mean, it's a really good project actually. And if you are done, you can leave the session. And yeah, please scan this for attendance. If you are done with attendance, just leave. Yeah, I
Yeah,
hope
the
this session
next
is
three
ended.
sessions will be really cool. We are
Okay.
designing the project. We also include PCB for that one also. It will be very cool. Maintain your enthusiasm. Will be waiting for you all. Thank
And
you.
we also post one assignment today. Like by like in by 5 p.m. we'll post one assignment. That is a really good assignment. And we included two projects in that. Please do that. They are really good projects, basic projects, but really good projects.
You can try to build those circuits. They are worth it.
No, like the request is for GPS project. Like there is nothing. I mean, only these 3 days topics are important for GPS project. So first, like these three, like PCB designing, a digital design session, and about IoT stuff. These 3 days are important for GPS project. So first we did these three sessions, and like these are some prerequisites for GPS project. Okay. So if you are good with this, I mean, if you attended these sessions, like if you attended the sessions and like understood everything, it will be very easier to understand this GPS project. Okay. The frequencies are like these three sessions only. Yeah, we will send you one G form for that today. By the end of the day, we'll send you one G form. You can submit your assessments there. Yeah, we will give you all that information, deadline of assignments and all. We'll post that in the group.
I think we can end the session for now.
Okay. If you're having any doubts, you can ask. Otherwise, just leave.
Yeah, yeah,
You
we
can
can.
discuss. Can this attendance? You can ask me doubts. If you're having no doubts, just leave. Yeah. We are from second year. Like our seniors guided us. So we learned everything. We learned everything by our seniors' guidance. After taking the session, after passing, you had no doubt.
Yeah, Anand, once the meeting is done, just share the recording in the group and slides someone else take care. I think that should be it. Yeah, they just end the meeting itself. Yeah, fine, guys, we can end the meeting now. Bye.
Yeah.